You guys are just a little bit more energetic and whatnot. So let's jump into it. Last time we met, we talked about a bunch of triangles which were famous for the lengths of their sides. We looked at the 3, 4, 5 triangle, which I can more or less guarantee you are going to see on your SAT. It's going to crop up. There was the 5, 12, 13, the 7, 24, 25, the 8, 15, 17. And really, each of those triangles represented families of triangles. So instead of 8, 15, 17, it might be 0.8, 1.5, and then the hypotenuse would be 1.7. Or instead of 5, 12, 13, it might be 500, 1200, and the hypotenuse might be 1300. Today, however, we are looking at just 2 more triangles, which are maybe even more famous than those. But these 2 are famous not for the lengths of their sides, but for the measures of their angles. I'm going to give it a second here because my computer wanted to reboot. And so now I have to go and turn it on, which takes a moment. Invite myself, send an email to myself, send, open up the email on this one, and away we go. Okay. And voila, this should do it. Okay, hopefully, yes, there we go. Okay, the first one is the one and only isosceles right triangle out there. It is a right triangle, so Pythagorean's theorem does apply. I said it's isosceles. I haven't told you which 2 sides are congruent, but it's got to be the 2 legs. You can't possibly have a hypotenuse be congruent to a leg. Otherwise, our if sides then angles theorem will get us into some trouble because we'll end up with angles which are congruent to the right angle and all of that. Since these 2 angles must be congruent with that if sides and angles, and all the angles have to add up to 180, these are both 45 and 45, and it's called the 45, 45, 90 triangle. I heard someone in my other class call it the 90, 45, 45. Sure, why not? Same thing. So until this moment, if someone were to give me the length of one of the sides, like this, I can say, oh, well, if 2 sides are congruent, then they have the same measure, so that is 10. And now I could go ahead and employ Pythagorean's theorem, a squared plus b squared equals c squared, 10 squared plus 10 squared equals c squared. And I understand that we know what 10 squared is, that it is 100, but I think it's going to be easier to think of this as 2 times 10 squared equals c squared. And we definitely have to do something more similar to that when we have variables as opposed to letters. And now to figure out what c is, I'm going to take the square root of both sides. If you want, you can literally write that. You might recall that the square root of a square gives you plus or minus, but we're really only interested in the positive one here. The square root of 10 squared is just 10, and the square root of 2 is square root of 2. So that is my answer. And really, that's all you need to know. I mean, we're going to do 1 or 2 more of these because every 45, 45, 90 triangle is similar to every other 45, 45, 90 triangle. So from here on out, when I see a 45, 45, 90 triangle, I don't need to use Pythagorean's theorem. You tell me what one side of that 45, 45, 90 is, that isosceles right triangle, then I should be able to tell you what the other 2 are without having to bug Pythagoras. Okay. I am going to do it one more time, however. Let's do it with, oh my God, that's a bad looking one, no big deal, with variables. So I'm going to plug in an x and an x. We're going to find what this third side is. I'm not going to mark it as x or something like that because that would be weird. And again, presumably for the last time, I will start with a squared plus b squared equals c squared. A and b are both x. I don't know what x squared is, so the only simplification I can do is writing that as 2x squared equals c squared. And without writing the square root symbol on top of each of them, I'm going to take the square root of both sides. And the square root of x squared is x. The square root of 2 is square root of 2. And so over here, I get x root 2. And there it is again. It seems to fit the same pattern. X root 2, 10, 10, 10 root 2. Sometimes people don't like variables and they just want to use kind of the reduced triangle, reduce it as far as it'll go, down to 1, 1, and square root of 2. Okay, so from here on out, I really do not want to see Pythagorean's theorem done for 45, 45, 90 triangles. It is a waste of time. You know they are all going to fit this pattern. They're all similar to this. So I might give you an easy question on a quiz, on a test, on your final, on your doctoral thesis, where I tell you that this is 17. That is, after all, my favorite number. Then as long as you have enough information to know that it's a 45, 45, 90, so I put in the 90 and the 45, that's enough. No choice tells me the other one's 45 as well. Without doing any work, you should be able to fill this in at 17 and 17 square root 2. Now, if you want to, ta-da, a little bit of flourish there. They don't all have to be in the same orientation. It's not so bad if I give you one of the legs. Again, I have to give you enough information so you know it's an isosceles right triangle with a root 2 in it. To go from a leg to the hypotenuse, I multiply by root 2, and that's not real hard. 5 root 2 times root 2, root 2, root 2, oh, is just 2. 5 times 2, 10. Now, I find it slightly more difficult, just barely, if instead of giving you one of the legs, I give you the hypotenuse and the hypotenuse has a square root of 2 in it. So maybe if I tell you that this is 8 root 2, well, then you can think to yourself, well, if x root 2 equals 8 root 2, then x just equals 8. Of course, looking at this later on, you won't know where we started, but it doesn't really matter. You can start from anywhere as long as you have one of them. Now, this is the one which is a little bit harder, but not downright miserable yet. What if the hypotenuse were an integer? And it's not so mean if the integer is even, and I'll show you why. Because to go from leg to hypotenuse, we multiply by root 2. To go backwards, we must divide by root 2. And I have a trick for this, so I never actually do it this way. But this is how it would be done if you wanted to divide by root 2. You'd say it's 10 divided by root 2. And then you'd look at it and go, oh, wait, that's not simplified. I'm not allowed to have a square root on the denominator. So I'm going to multiply both the top and the bottom by the same thing. Anytime you multiply the top and the bottom by the same thing, you're technically multiplying by 1. It doesn't change what the answer is, it just changes what it looks like. And root 2 over root 2 times root 2 is just 2. And that simplifies a little bit to 5 root 2. But there's an easier way. When I have to divide by root 2, I don't. I just divide by 2 and multiply by root 2. So 10 divided by 2 is 5. 5 times root 2 is 5 root 2. So it really takes no work. Maybe some of you recognize that these two triangles are congruent and did even less work and just said, oh, the hypotenuse is 10. We know that triangle. So it goes. I am really specifically not looking for much work here. You should be able to do these. Bam, super quick. Of course, I could be meaner. I guess there's no upper bound to how mean I could be. It's slightly meaner to make this not a even number, but an odd number. If I made it 13, then this would be 13 over 2 times root 2. As I said, there's no upper bound how mean I could be. I could make this 17 root 3, at which point you'd have to divide by 2, 17 over 2, and multiply by root 2, so I'd get a root 6 there. Sorry, I saw something in the chat which disappeared too quick for me. Could you go over the 8 square root triangle and the first 5 square root 2? This one here is the first 5 square root 2. So the idea is that these are always similar. And admittedly, sometimes when I'm going through a million of these, I might forget to mark things congruent and whatnot. These are always similar to this triangle, x, 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 root 2. So if you started with a 5 root 2 over here, then I could say, oh, okay, well, that leg corresponds to this leg, or that leg, doesn't really matter. And say, all right, so 5 root 2 is to x, as x root 2 is to this. Well, what do I do to go from here to there? You always multiply by a root 2. So all I'm doing is multiplying by a root 2 to get the hypotenuse. But of course, that simplifies. Root 2 times root 2 is just 2. So I should end up with a 10. And works the same way in reverse. If I knew that this were 8 root 2, well, this is always that without the root 2 on it. I'm getting rid of the root 2, which to most people sounds like I'm subtracting it, but it's multiplied on. So to get rid of it, I'm dividing it. So to get rid of it, I'm just dividing by root 2s. I get an 8 in. Okay, that was one of the 2 famous triangles, but that was kind of the B-level celebrity. Here comes the A-level celebrity. This is the one. Get your autograph books ready and whatnot, because this is presumably the most famous right triangle out there. In fact, we shouldn't even start with it. That was silly. Let's start with one that we've seen before. I don't want to get too struck too quick. So let me try my best to draw what looks like an equilateral triangle to me, which means it's also equiangular. I'm going to write a 60 here. And then I could write a 60 here, although I don't really need to. I'm not going to write a 60 at the top, however, because in this equilateral / equiangular triangle, I am going to draw the altitude. Altitudes necessarily form a right angle. Well, it's not just an altitude, it's also an angle bisector. You could probably use the no choice theorem and go, oh, okay, or just use the fact that the 3 angles in a triangle add up to 180, figure out what this other one is. And it's also, in addition to being a altitude and an angle bisector, it's also a median. So it's splitting this thing into 2 congruent bits. And I kind of lied, because disguised in my equilateral triangle were two twin 30, 60, 90 triangles. They were there all along. You just didn't know it. Maybe you did. I don't know. Okay, so there were these two 30, 60, 90 triangles hidden in there. The key is that this, I told you it's an altitude, and I mentioned that it's a median. Remember, a median bisects the side of a triangle. And it was an equilateral triangle to start with. So it makes sense to me, since I'm going to be bisecting one of the sides, not to call each side length x, but to call each side length 2x. So that when I bisect it, that part, which is part of my 30, 60, 90 triangle, is x. And I'm going to mark this as h for height. Although if I turned it some other way, it wouldn't make so much sense to call that the height. And I'm just going to bug Pythagoras one more time today. I said it was the last time for 45, 90 triangles, but one more time for these to get what the relationship is between these x's, which are floating around, and that h. So one last time here, I'm going to say that a squared plus b squared equals c squared. My legs are x and h. I square them both. And my hypotenuse is 2x, which I square, and then I point out that I made a mistake. Oh, it looked like Ella was going to tell me. That looked like a hand. Yes, go ahead.
I don't know your mistake, but I was just wondering if you could repeat why it's 2x.
Why it's 2x? Well, it was our triangle. We could have called it whatever we wanted to. I could have called it, like y or something. But then when I bisect the side, because this side is congruent to that side, it's an equilateral triangle, this would be 1/2 y. And I did not want to play around with fractions. So, I could have called it 10x and that could have been 5x, wouldn't have had fractions, but why the big numbers? So, knowing that I was going to split it in half, I thought it would be wise to call this one 2x, and so that one can be x. Okay, so we're back at it. I do still have a mistake in this equation. Brock faked me out. He did one of these things. I thought he was raising his hand for a moment. Oh, yes, Kira, thank you. I saw two hands. Dang it. Yes, Kira, go.
Yeah. Do you need the parentheses around the 2x so that it's not like 2 and then x squared instead?
I'm looking over at Aaron. Aaron, what do we think?
I was going to say the same thing.
Okay, I thought I saw a little bit of a nod in there as well. Perfect. The two of you guys. That is absolutely correct. What am I squaring? I'm squaring the length of the side. What is the length of the side? The length of the side is 2x. I better square that. Yes, indeed. And so when I do that, I get x squared plus h squared equals, I have to square the two. I get 4x squared. Let's subtract an x squared from both sides. So now I only have 3 of them over here. And when I take that square root, I hope people don't mind that I'm going to not actually draw the square root. I'm just going to take the square root of both sides. I will get that h equals square root of x squared is x. Square root of 3 is root 3. I really appreciated written x root 3 instead of root 3x, because if you do it the other way, it's really hard to see what is in the square root and what isn't. So that is a relationship between x's and h's. If I knew what this is, I would multiply it by root 3 to get that. Do you have to make the side of the triangle 2x each side? Is this important? It kind of is. And that is because what we have discovered here, and I'm going to do the one with variables first, is that in every 30, 60, 90 triangle, which I just find easier to draw kind of like this, the side opposite the 30, I can call x. The side opposite 90, is 2x. And the other side is x root 3. If I put a 1 over here, you might think, this isn't so hard. It's as easy as 1, 2, root 3. Nope, no laughing, nothing, not as easy as 1, 2, root 3. Sad for me. I thought it was funny. Okay, thank you. I think that was a charity laugh emoji, but I will take it. I'll take it. I'll take what I can get. So that's really it. Every 30, 60, 90 triangle is similar to this one. Again, if you wanted to, yeah, you could call this 1/2 x, and that x, this would be 1/2 x root 3. So for people who don't like that 2x, we could get around it, but it just, it feels like this is a whole lot nicer. Let's see it in action. This one has, it feels like more combinations than that last one. And again, to show that it's a 30, 60, 90 triangle, I don't actually need to write a 30, a 60, and a 90. Any two will do. If I told you that this were, someone pick a number, show me a number of fingers, or yell out a number or something. Yes, thank you, Wyatt. 2. If this were 2, then I can tell you without doing any other work, just double it and get 4. Go back to that 30 and multiply it by root 3. And that's all you need to do. So take what's opposite the 30, double it, make it the hypotenuse. Take what's opposite the 30 and multiply it by root 3, and there is the other leg. And it works out nicely. I'm going to go back to this one. It works out nicely. The smallest side is always opposite the smallest angle, like it has to be. Sometimes people think that root 3 might be bigger than 2, but remember 2 is root 4. So opposite the 90, which is my biggest angle, is my biggest side, and opposite my mediumest angle is my mediumest side. Okay, let's look at a few different iterations of this stuff. I don't know if you can hear, but I have a mad baby wandering around yelling at things. Ooh, she wandered off. Okay, that was close. That's close. This time I'll just say 60 instead of 30. Works out just fine. If I told you that this were 12, now that I gave you the hypotenuse, since the hypotenuse is always double this side, oh, that's not so bad. This side is just 6. And once I know this side, I just multiply it by root 3 to get the other leg. And that's all there is to it. Now, as I said before, there's really no upper bounds onto how hard and mean and whatnot I could make this. Can I open your door? I'll open your door, little bug. No. Do you want to wave to my class? No. Okay, don't wave to my class. I'll be right back. I'm going to open the door. There you go. You're welcome. She hasn't mastered doorknobs yet. No upper bound to how mean I could make these. I mean, I could only give you this side and I could make it some expression. That seems really rude. But these are about the standard ones that I do. Not real mean. I could tell you that this is, well, I just did that. We'll make it 16 root 3 instead. And again, I do need to give you enough information so you know it's a 30, 60, 90 triangle. Well, if opposite the 60 is 16 root 3, and to go from here to there, I multiply by root 3. To go backwards, I divide, and that guy's a 16, and this guy's a 32. Okay. A reasonable about meaner would be if I made the side a 9. So now I have to divide by root 3. Oh, wait, we learned something about dividing by a radical. Don't divide by a radical. Divide by the number in the radical, and then multiply by that radical again. So to divide by root 3, I'm going to divide by 3 and multiply by root 3. Dividing by 3, I get a 3. Multiplying by root 3, I get 3 root 3. and then just double it to get that. And then I could just be downright rude. I could tell you that this side were 7. All right, so I got to divide by 3. Well, that's 7/3. Rude. It was rude, but was it hard? I mean, it's ugly looking. Nobody feels good about themselves when they get their answer to be 7/3 root 3. And for that matter, 14/3 root 3 is the hypotenuse. But it's not so horrible. Okay, I have not gotten a lot of feedback from you guys. How we feeling on this? Good, bad, somewhere different? I got some thumbs up, got another couple thumbs up. Awesome, 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 awesome. So it's really just about fitting things to those patterns. Now, where might these things crop up? Just about all over the place. So let's open up our packets. On my packet, it's page, I think, 35. I'll show you what mine looks like, and hopefully it'll be your page 35 as well. So back to you guys, share screen, this guy, and share. Let's take a look at these guys. Print out these. I'm going to turn that guy back on. If that's a 90 and that's a 60, this little guy up here must be a 30. So if opposite the 30 is 4, then opposite the 90 is double that, and C should equal 8. Now, I can use Fibonacci to figure out what A or B is, but I really don't have to here. If opposite the 30 is 4, then opposite the 60 should be 4 square root of 3. Using some of my Fibonacci techniques, I will notice that this is a 60-degree angle. I can go to that one, and this is a 30. And this medium triangle is also a 30, 60, 90 triangle. If opposite the 30 is 4 root 3, then I multiply that by root 3 to get the other leg. 4 root 3 times root 3 is 4 times 3 is 12. Okay, got some nods there. I know that this is kind of small. Let me zoom in a little bit and focus it. That helps a little bit. Over yonder, I've got another 30, 60, 90 triangle split up with an altitude to the hypotenuse. That is going to make that a 30, that a 60, that a 30, and that a 60. And that is a right angle as well. Notice I have a small, medium, and large triangle. I know in my small triangle that the hypotenuse is 12. That is double the side opposite the 60. The side opposite the 30, excuse me. The side opposite the 30 is D. D should be 6. And if I know the side opposite the 30, to find the side opposite the 60, I multiply that by root 3. I get 6 root 3. I've got now one side of the medium right triangle. I've got the side opposite the 30 is 6 root 3. You get the side opposite the 60. I would multiply that by root 3. So B is 6 root 3 root 3. Oh, well, that's 6 times 3. That is 18. To get the side opposite the 90 in the medium right triangle, I'll take the side opposite the 30 and I will double it. So C equals 12 root 3. And I could get E in a variety of different ways. I could just add up B and D, but I'm also going to look and say in my biggest triangle, it is the hypotenuse, and I know that in my biggest triangle, 12 is opposite the 30, so I could just double it and get 24. By the way, in my biggest right triangle, if I took the side opposite the 30 and multiplied it by root 3, I should get C, which is 12 root 3. Perfect. 12 times root 3 is 12 root 3. So it all works regardless of how you look at it. 24, of course, is that 18 plus 6. We're all good. Okay, that one I thought was reasonably difficult. A lot of stuff going on. Number 3, on the other hand, you should just be able to look at and go, oh, 12. In number 4, if you said that the side opposite the 30 was 28, then you didn't notice it's not a 30, 60, 90 triangle. In fact, in number 4, I would like you to recognize that this side is 7 times 4, and this side is 25 times 4, because this is a 7, 24, 25 triangle. So this is 24 times 4, which I think of as 25 minus 1 times 4, which I think of as 100 minus 4, which I think of as 96. And speaking of them being tricky, over here, it looks like a 3, 4, 5 triangle, just proportional to it, but square roots are not proportional. So we have to actually go to Pythagoreans here. Root 3 squared, root 4 is 2, but doesn't hurt to write it as root 4 squared. 3 plus 4 equals c squared, and c equals the square root of 7. So t, which is my hypotenuse, is the square root of 7. Okay, and that pretty much runs us out of time